Welcome back, people. Today we are going to try and code a different version of transformer networks, which is inspired from the graph neural network concept. Because at the end of the day, transformers are basically graph neural networks. So let's begin. So I'll first explain what I am trying to do here, which is if you think about a transformer network, then you might think that it's a feed forward neural network, etc., 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 but it's basically a graph network where the feed forward part happens on each and every node. So if you consider, so you can consider BERT like a fully connected graph network where all the nodes are connected to all the other nodes. In GPT, you have a forward connected network. What that means is, like in this case, the at time step t plus 1, whatever value happens, or whatever prime, it's not exactly, now you can define it as t plus 1, but there's a lot of ways of defining it. So right now I'm just saying that whatever was the input of a, once it goes through the multi-head attention, it gets the output a prime. And just a minute, let me just close the window. Much better. Yeah. So whatever is the input a, the output a prime. Right now a prime is basically what is supposed to be at b, and b prime is supposed to be what is c, and c prime is whatever happens post c. Now the way to think about it is you can actually fix it up, and yeah. So now the adjacency network, right now you have a 24 cross 24, 2048 cross 2048, a very big matrix, and in that matrix you apply an attention mask, which is a you mask out the top right of the triangle of the matrix and say that this you cannot attend to this particular value. Now other way to think about it is that if you have a particular network, then it's just, if you have a graph network, then one node is connected to all the nodes as the source, and all the other nodes become the target. For the next one, it is the source for all except the first one. Just a minute, I'm getting a call. So what I was trying to do is it possible that if we interpret this model, if we interpret transformers as a graph network, then it actually becomes a lot easier to process, because now you can utilize the structure of a transformer network, which is at its core a linear for query key value, then then you perform an attention matrix, which is this piece, and then you perform a projection, which is the MLP, that is 1 cross 4 cross 1 times 4 times 1, and then you add it, which is the residual connections, and finally you update the original values. Now the trick right now is that the way I have applied it is that currently works just for one particular example. It works just when you have batch size of 1, but it does not work when you have larger batch sizes. So I have a simple network, which is a transformer conf block. It is in fact inspired from this paper. Stuck here. They do call it like the so they do call it the graph transformer, and they also have a gated residual thing, but it's not the perfect representation. It still uses all the message propagate from dot geometric. Is it a way that you can simply bypass all of that? Now that's the problem that we're trying to solve today. So think of it like this, where you have the x as the node feature, a are the edge attributes, and y are partially observed labels. This also is the perfect representation of what a language modeling system does. Is that if in case you have a BERT, then all of these things, all the edges are connected to all the others. You have 85% of the values are partially observed labels, while the 15% are actually those mask values, and then you simply propagate them through, and final outputs you predict the unlabeled nodes, which is what happens during inference. But during training you also take all the final outputs and you apply the oh, there's a spelling mistake, interesting. You train it based on that. Okay, so this is where we are right now. You have the layer norm. This is ln1. So ln1 is for all the inputs. Then ln2 comes, yeah, where is ln2? Oh, ln2 is for all the edge attributes. Now transformers is actually a subset of graph neural network. It's a very specific kind of graph neural network where there are no edge connections. That's it. And for GPT you have forward connected networks, and in case of BERT you have fully connected networks. So this is what a transformer is, but in our case we can also have some edge attributes. Then this is the linear for query, and linear for key value. Now I have observed that in the Hugging Face interpretation of the code, in the Hugging Face code, that is what they also do in GPT-2, is that you train one network that has that's like 1 cross 3. So you take in one embedding, get it scaled up to 3 times, and then you simply split it and say whatever that this is the key value and query. We can do that as well. That's possibly one permutation we can do. But right now what happens is, because of the graph neural network structure, you decide that you need to pick up these values. You just need the x indices, which is xi, and you need the y indices, that is the source and the target. And so you have a as you can say, you have a subset of the entire network. So your entire network would actually utilize an E cross E system. Let me just close this piece, or I'll just bring it down here. Yeah. What this model does is it identify the, I should just update this thing here. Go from n cross n to E cross E, where E is the number of edges. This way you can actually reduce the computation by a very large factor. Now this does not help in language modeling tasks because E is equal to n, and so you can get away with it. But for a lot of problems, n E is smaller than n, and so you can probably get a speed up. Yeah, go from, so you select only the indices that are in this thing. You perform the linear for query, you get the one for edge, you update the query with edge attributes, you perform a KV1, and then you split it into key and value, and then you simply say split heads. What split head does is it breaks it into something like this, either BHEN or BHNE. Basically splits it into multiple heads. You pass it. Oh, I think I messed up somewhere where I did not actually merge the heads. Interesting. And it's still working. Crazy. I need to add the edges somewhere here, and I have not done that, so I'll need to see what I am doing wrong. Oh, there's a lot of code that is wrong here. Anyway, yeah, you pass it through a layer norm and a residual connection, then a layer norm. Similarly, you do a projection, which is the MLP 1 cross 4 cross 1, and then you add the residual connection, and then you apply a scatter mean. Scatter means are special functions. Scatter, these are brilliant. I mean, this is a torch scatter code, PyTorch scatter, and all it does, it helps you to perform this kind of tasks. Given a particular input and given a very big index, you can actually merge these things in different formats. So this is what it helps you do. The code is written in complete C CUDA, and the advantage is that this is basically a JITable function, which means .jit. It compiles the code at runtime, or aka what you call is just in time, for it to run either on CPU or on GPUs. Okay, so you do all that, and finally you update. So now you have to update the n-crossdim from the e-crossdim that you have because of this piece here. You fetch only those values that are required, but now you need to update only those values that are now required. So the flow of information is from source to target, so the targets get updated. What I mean by that, this is the target, and so these are what get updated, not the source. So the first thing we are going to do is we are going to fix a couple of bugs in here. All right. Okay, the number of dims don't match in permute as index. Oh wait, yeah, it's correct. Okay, so this is the key that it predicted, which is supposed to be 1146. What? No, this is the dim. Yeah, these are supposed to be your key and value indexes. So this is your source 1211. So you have 0.77 this, 0.77 this. Yeah, so you can see 0.77, 2.4, 0.77, 2.4. So you got this piece. Now you have the correct key and value. So now all we need to see is print Q plus E is equal to Q, or more important, Q dot size, because the values are anyways going to not understandable. So you get a 1.1146 head. Now why is that? So the value of K is also incorrect. So the K value you're getting is 1146, whereas the value that you should have got is 146. Now this is the primary problem that I'm facing when you start converting these things to batch. So if I just do this, you see it actually works. Oh, it doesn't apparently. No, it does. You see you get a 126 kind of matrix, but if you actually batch it, you're not going to get the correct value. So you get 1146. If I actually do a 2 thing, then what is the value that is getting updated? So it's giving you a 2246. What are these values? So you have 1212000122 So you have 1. None of these values actually match. Yeah, so you have 1, you have 2, you have 1, you have 2. So this piece is done, and you have 0112. Also, it's taking this from this thing 0112. Okay. So what it is doing is that it's taking the values right from it's filling the values for each and every batch. Now that is not what we want. This value corresponds to a different batch, and this values are for the first batch, these are for the second batch, so on and so forth. So we need to fix that here. Now there's one way I think we can do it, is if we use an nn.embedding from pre-trained. So by this way it manages all the embedding piece. But if I just had to select torch select by index. Yeah, index select. Cool. Torch index select. Now the way we are going to actually test out or experiment with it is like this. X is equal to torch dot random. You have the inputs are, say, batch size of 2, 5 nodes, and each has 3 embedding dimensions. So you get a data like this. Clearly makes sense. And now your edge index is going to be torch dot tensor. Yeah, torch dot tensor. And because you have 2 batches, so let's just say 0 0 1 1. And let's just use this instead. Much more simpler. Alright, so torch dot select index x, yeah, index select. Okay, index copy, index fill, index put, index select. Interesting. Index select received an invalid combination of arguments, got tensor but expected one of tensor dim tensor. Okay, so the dim is going to be 1. Oh, index is supposed to be a vector. It does not do batch select. Masked select returns a 1D tensor which indexes the input tensor according to Boolean mask. This is a bool tensor. No, we don't need that either. Torch batch select index. Batched index select. PyTorch batch indexing. Efficient batch index select. Yeah. And so you have a tensor which has a shape 8 cross 24 cross 2. So 8 is my batch size. Makes sense. 24, and you have 8 things. I would like to get the data from every batch at the following locations. Torch.gather. Output torch.arrange. Okay. So yeah, this is what is happening. If I just do this, what it is doing is that it's returning me this value for each and every batch. So instead, if I, as this guy says, I can just do torch.arrange ei.size 0. ei.size, yeah, it is 0. So this value is 0 1, and oh wait, yeah, so it works because at each size you have just one specific index. Yeah, it does not work if I have a batched index. Gather. Torch.gather. Alright, this is one before edge stack. We should have probably studied a little bit more. Okay, so you have torch.gather. Torch.gather x. Yay, we need to pass dim. Just one size does not match. Expected index 2 to 4 has to be smaller than this thing. Size does not match at dimension 2. Of course it does not. Zero, zero, 1, 0. Okay. Past index select. So what does this option do? X1, yeah. Expand long tensor. This says the number of sizes provided 3 must be greater than or equal to the number of dimensions in the test tensor 4. Let's also try the nn.embedding thing. So I can just say x is equal to nn.embedding.from pre-trained, and I can just say x. What is x? Embedding parameters expected to be 2-dimensional. Yeah, supposed to be 2-dimensional. Okay. I'm meeting at 3 o'clock. Yeah. So one way that you would do it, if I had to do it the brute force way, the way you would do it is something like this. You have x, cool, x is same. You would say torch dot cat, and you would pass a lot of tensors, which is x of I, and you would say ei I0 for I in range x dot size ei dot size 0. Yeah, so you have x, you have dim is equal to 1. Only integer tensors of single element can be converted to an index. God damn it. 0, 0. What is 0, 0? I should be able to do it, man. Come on, man. Come on. Slice and dice must be integers or none, or have an index method. Yeah, so this is what it's going to work. Only integer tensors of single element can be converted to an index. So how the fuck am I able to access it here? Are these guys crazy? my x is on 0. This is my x0, and of these I want these elements. Similarly, of from this thing I want these elements. So the way you would go about writing it is you have x1 and then you would say 1 comma 0. Oh, so this works. All I have to do, oh shit, sorry, it's working now. Yeah, this is how you go about it. I think so. Yeah, so you have three things. Your dim is supposed to be 0. So you have gathered 0 1 0 1 0 1 1 2. Cool. And then you can say dot reshape ei dot size 0 comma -1. No, you would say -1 ei, no, x dot size -1. Cool. Yeah, so you got this matrix right. So this is what you can put, we can plug right here. Ah shit. So you have def collect, you have self, you have x, and you pass the indexes of all the values that you want for this x from ei, and then you return this thing. Cool. So this is tosh.cat. It still has the gradient, right? If I do require grad is equal to true, table of instance pin number requires grad. Okay. Ah, cool. So I do get the consistent gradient, which is grad.view backwards. And if I so this is going to be my out. Cool. And if I do out my L is equal to out minus np dot once like out, this is my L maybe. Oh, sorry, not np, torch. Cool. And I can just do L dot backward. Grad can be implicitly created for only scalar outputs. Oh, sorry, my bad. L dot mean dot backward, and if I do x dot grad, I do get the gradients. Nice. And you can see the gradients are only applied on the tensors we actually want them to be applied on, not on all the tensors. Nice. So this thing works. Cool. So this is how you would collect. Now what you're going to say, we want self dot collect, we pass it the x, and then we also tell it that the edge index list, this is the edge. Oh wait, yeah, this is what you would pass it, and then you would say q is basically the same thing except this thing is 1 now. Alright, perfect. Okay, so now you are getting pretty consistent values. Cool. Cool main. Now q dot size is 246, which is correct. However, k dot size is still incorrect. No, wait. We have dash. I should have better. Okay, so you have a dot size, and a dot size is 2146, and so we need to now pass it through the merge heads thing. What that means is you are going to do this. Let's do it after this. A is equal to self dot merge heads a. Yeah. And we simply print if a dot size. Okay, so what is the X out? This is X out. Not that I understand any of it. Copy slices. If I have grad function copy slices, what is copy in place operations with this thing? I was wondering how to deal with in place operations as in PyTorch, as I remember using in place operations with AutoGrad has always been problematic. Set item. Alright, so let it be this for now. Let's read a little bit about setting. PyTorch moved in, and none of this is okay. You have put 252 put. What is torch dot put do? You have torch dot put. Now index put. What is this? Torch dot index put. My god, my laptop's going berserk. How much is my video uploaded? Oh, it's already 54 minutes. Sorry, uploaded 54%. Yes, I am uploading a new video. Not that people are watching this a lot, but meh, it's fine. Okay, and okay, so you can do, I copied the examples without doing fixed brackets until yours was swapped. Index put does this, index put does this. Index is a list of x coordinates of insertions and y coordinates of insertions. The values may be a single value or 1D tensor. Yeah, so what is this thing? Unnecessary unnecessary mem copies emitted by this thing. What is this? Using view unnecessary mem copies emitted by AutoGrad engine. Using .view actually changes the dimensions of the model. Instead introduces 4 extra mem copies of size this. Pillsbury, blah blah blah. So I just do copy slices. Try to avoid copying copy slices and as started backward in favor of operations when possible. This is a bit tricky but doable, at least for some common cases. Specify an explicit derivative for matmul instead of differentiating the individual operations. This would avoid treating the output as view of another tensor. Linear, blah blah blah. This is super old code, man. Come back to this. So if I do this, and so you can see that it does not update all the values. So or does it? Oh, it does. Don't you asshole. You do update all the values. Asshole. Yeah, but you know what? So X here is this thing. Oh, it does pass to the X linear now. No, it does not. So X original is the value that gets updated. Yeah, instead of this, let's just also write one thing, which is X is equal to X orig. Alright, so now see, the problem right now is that it's still updating all the values of X even when I've explicitly told it that does not. Ah, shit, the updating won't work correctly. Collect. You need to experiment with put index. Okay, so X is equal to torch. Can I just define a function? R&D is torch dot random. Yeah. So I have X is equal to R&D 2, 4, 3. So you have this thing, right? And then let us have a particular value y. Y is also this thing, but we don't want to update all these values, so y is actually going to be cool. 0 and 1 are the indexes that we need to select. So you can see what it is going to do is for this index and this index, so for this row and this row it is going to update these values. For these two rows it is going to update these values. Now that is what it is supposed to do, but let's see. Torch dot index fill. What does index fill do? I don't think it's here. Indexing, slicing, joining, mutating ops. Okay, so index select returns a new tensor which indexes the input along the dimension dim using entries in index, which is a long tensor. Cool. Where random sampling. Okay, index. So index select. Where is index put? Tensor dot. Oh, interesting. So yeah, index put out place version of this thing. Tensor corresponds to self in tensor 1 corresponds to self in torch.index. Oh, okay, cool. So we are going to be using this, Push the values from tensor value into self using the indices specified, which is a tuple of tensors. The expression equivalent to tensor indexes value. Cool. If accumulate is true, the elements of value are added to self. If accumulate is false, the behavior is undefined if indices contain duplicate elements. Do we have source? How do we go to the source? Index fill fills the elements of self tensor with value well by selecting the indices order given in index. Yeah, so you would like to use this, right? No, actually you would not. Puts values, fills value. What is the difference between these two? And then you have the index copies element. No, we don't want copies. Put versus fill. Oh, sorry. So val is basically it's supposed to be a particular value. Put is where you have value is supposed to be a tensor. So we are going to use index put. Okay. Cool. So you have torch dot index put. Now you have x dot index put, and indices are 0. Oh shit. 0 0 and 0 1. Let's just try with a 0 0 first, and your value is y. Oh shit. Tensor dot long must be a tuple of tensors, not a tensor. So 0 0 0 and 0 0. The value of tensor of shape 2 to 3 cannot be broadcast into indexing result of shape 3 3. Yeah, we are not going to do that. What we're going to do is instead we're going to say no, so 0 0 0 is this. No, we want this 1. It's going to be 0. Cool. So you have okay, cool. So what has happened is you have put this and this in the first index, right? And you have not changed anything. If I just do an px, what is the value? Okay, so it's an in place update. Okay. Now if this is just for the first index. If I have what happens if I do this? Alright, and I can just do 1 0 and 1 1. Then I can just put in y. No, it doesn't work. Okay. Oh no, wait, it does work. It did work correctly. So at value 0 0, it did put the correct order, and also 0 1. It was supposed to put minus 3.3. Okay, so it did not do that, but then at 1 0 it was supposed to put this value and it put it here. What is happening right now? It's a tuple of tensors. Tensors used to index into self. Well, that is what I'm saying, man. You have to go to 0 0, which is this piece, and update it, and also this piece which you have not updated. It has, however, updated this piece, which I do not understand how it did that. Okay, so what it must be doing, it's going at 0 0 of y this. I can just print it. 0 0 of y. Okay. No, I don't get it. What? So I have a 0 1 0 1. What if I just do this? What happens if I do this? So you do need two-dimensional arrays here. Okay, if I do 0 comma 1, and I can again just do 0 comma 1, I can do 0 0 and 0 0. Not a sequence. Oh shit, sorry. My bad, motherfucker. My bad. Alright, so 0 0. So these are supposed to be all the x values, and these are supposed to be all the y values. So it's going to 0 0 by updating the value from here. Just one. No. It's updating the value from here. Wait. So at 0 0 it's supposed to fill value from 0 1, which is what it is doing. It's going to 0 1, and no, god damn it, is the behavior even the same? I mean, well, it is. Fill values. Well, in a way, the output of this thing is anyways going to be it has a 0 0 value, so I'll just show it to you. So if I just do this, yeah, oh, you son of a bitch. X edge. Is the K even correct? This is supposed to be the K, and it is correct, is it? 1 2 1 2. There you have 1 2 1 2 and 0 1 1 2. So you have 0 1 1 2. So K is correct. K is correct. Q plus E, my assumption is also correct. And if I pass it through, oh fuck, I know it's going to break now. That's another full set of bug in our code. It's not able to support matrices that are bigger than a certain value. Like it has to be fixed. Everything has to be square. It does not work otherwise. What if I have two heads? Does it still work? Oh yeah, it does work. Cool. Yeah, sorry about that. I had to go somewhere. So let's get back to this. So this piece works fine right now. This entire thing works fine, just fine. Cool. Cool. So now fixed one issue where I can have any number of things. Right, so I can have these many tensors and it's still only going to update. Select few of them. The problem is that it is updating all of them, whereas it is only supposed to update a few of them. So in this case, it is updating. So I have 0.647. So it is updating only the first three values of it, which is not true. It needs to update. These values, which is these two values. It needs to update these two values, not the rest of them. Now this is also incorrect. Ideally all the values should be updated, but the reason we are not updating those right now, or not adding, I haven't added the code for it, is because then we would have never been able to know that there's a bug like this. So we'll be updating, we'll be working bottom up. Okay, how does put indexes work? What is this? So this is not our use right now. No, I don't get it. Put. Well, the beautiful thing is that instead of using index put, we can just use put. Okay, so if I had to first, indices is supposed to be this thing, right? So if I had to put it this way, how would I actually put it? So this is the selection piece where you go over all these values and you put them like this. The other way would actually be so you have for I in range, this is going to be batch x dot size 0 x b, yeah, say this is not work, x b and values 0 comma 1 is equal to y b 0 comma 1, and then you can just do x, and you can see this thing has updated these values. Now another way to do it is I can actually specify randomly. Yeah, I can just do this two thing, and now I no longer need to select the index. I get this, and I can actually select EP, which is index of put is tart.tensor, and I have let's just take these values for now. And dot long, and I do it like this. EPI is equal to this thing. Oh, 1122. Oh wait, this is not correct because we do need to add means. Yeah, so this is going to be 0 1 2, and yeah, see, the problem is that this is not the correct matrix. The kind of matrix that we are going to get is, it's going to be more like this. So you have for 0, we're going to say 0 2 and 3 is equal to 0, and for this all I have is 3 equal to 0. Cool. And now what you're going to see is that, yeah, so this tensor is completely fucked up. It's wrong now. We need to do an mean addition. X is equal to x. What is x plus y? Right. Now this is not correct. Is we need to x dot mask is equal to y not equal to 0, and you have y. Oh, what the fuck is t? Value is equal to y. String form. Oh, this is the value of x. Cool. Kill. What is this value? Okay, got this, and Yeah, so you have this value. First off, so x can just be defined as torch.where. Now that is not a big deal. You can just actually just do this torch.where, and you have y not equal to 0. You pick the value of x. If it is not equal to 0, you pick the value of y, or else you pick the value of x, and you get the correct in place updated values. Now I need to define something else, which is just to check. You have requires grad is equal to true. You get where backwards, and you can actually, so this was x, you can actually define it like this. Right, and you can define L dot mean dot backward, and you can do x dot grad. Cool. Now this ain't right, because the gradient so what is happening is all the places where you should have received a gradient, you are not. If you do requires grad is equal to true. No, y in very realistic terms is just going to be some noise. Yeah, so now you're getting some value. Now you can see what is happening is that you multiply it by some random constant, so you do get this value, and then you take the entire output and you update all the values, so you do get the correct gradient. Now the reason it worked, so is this correct? I only take the selection. Yeah, this is correct, because if you're only going to select 1 and 2 from this thing, the gradient for the rest should be 0, and if you're going to select 0, 1, 2 from this, the gradient for 3 and 4 should be 0, which is correct. Oh yeah, just a minute, I have to update someone on the meeting. And someone else as well. No, not Slackbot. Yes, what? Can someone give me an update on the walkthrough? Start finalizing the tasks to complete. Cool. So I have 30 minutes. Let's get this done in 30 minutes. How far has my upload come? Oh, it's almost there. Cool. Alright. So this thing works, this thing also works, which means now what we have to do is we can just select torch.where. Yeah, the values are not 0. So this is going to be replaced by torch.where. Cool. And then we need to see what's up with scatter mean. So you get this a size and x edge. What the hell is x edge? What the hell am I getting x edge? Oh, here I'm getting x edge. So this is x edge. Yeah, this is not x edge. This is just out. Hidden. Let's just call it hidden. This is my 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 hidden. Cool. Okay, so this is my final hidden value. The problem is that this okay, so this thing has no knowledge of where to actually pick this from, right? Am I correct in my is this my correct assumption? So the way this is working is, you can see what it has done is you have 1 1 2. Okay, so wait, you need to print what is the hidden here. So we are going to do that. Oh, what is it? This is wrong syntax, mate. What you doing, mate? So you have this thing. You take the mean of these two. No, do you take the mean of these two or what? You have 1 1 2 2. Why is it returning 3 values then? Similarly, you have 0 1 1 2 2. Okay, when you have 0 1 1 2 2, you have 0 1 1 2 2. Okay, so if I do a mean of these two, what do I get? I do this plus I do this. What do I get? And if I do this, oh no wait, BODMAS, man, BODMAS. Don't you know the BODMAS rules? So I do get this, and when I have 1 1 2 2, however, why is it fucking up? 1 1 1 1 2 2. Yeah, so I am telling it that these two are for matrix 1. What that means is, yeah, so there is some issue with scatterad. Let's debug scatterad now. So you have scatter mean. You're going to have a function which is rnd x is equal to rnd 2 comma 3 comma 4, right? You have this thing, and you do know, no, this is x comma 4 comma 4, right? Yeah, you have 2 comma 4 comma 6 basically, whatever. 2 comma 4 comma 3, this is your this thing, and my indexes idx is torch dot tensor, and then you have the values 1 1 2 2, and you have the values 1 1 2 2 and 0 1 2 2. 0 1 2 2. Cool. Along this thing, and you do scatter mean, you do an x, and you also pass it the dimension on which you need to do it. So yeah, this thing is idx, and this is going to be 1. Okay, so you asked how we actually fucked up dimension should be 1. Alright. Alright. Is it correct now? 1, 1, 2, 2. It is clearly not correct yet. Batch size, number of nodes, embedding dimension. This is 1, 1, 2, 2. So yeah, I get this. How is it determining the value for this thing now? So it does say 0. I need to probably read a little bit more. Scatter add. Scatter mean. My god, my laptop is like, holy shit. Oh, it's live. See, still processing the HD version. What should I do? Should I put myself? Should I put the sexy graphs? Just this? Probably put myself. Cool. And save. Let's just go back here. What are the kind of views that I'm getting? It's supremely awful views. Some of them are good. Like on one video I did get 229 views. So it's super weird, man. Channel videos. Meh. Anyways, so processing the HD version. I'm gonna minimize this. Apparently just keeping the window open consumes the battery like hell. You can see how like, this entire fan noise is coming because I simply opened the tab on Windows. How ridiculous is that? Okay, so I do have this. Now my problem is how am I getting this? This. So let's just work like this first. Plus I have this. Okay, so I understand why I'm getting -5 and -8.7 here. Now if I take this and this plus this, I'm getting this thing here. So if I actually have this, what is going to happen now? So it's going to always put it at the value at this particular value. Cool. What that means is I am going to get, I should get, well in the first place I should get this as 0 is because I do not have, oh wait, so hidden does get processed, right? This is my hidden value, so I do have some value and it is compressing it correctly, but I do not need all the values of hidden because people, I need to copy these values to certain locations here. Now what it is doing is I have the X out. Oh yeah, so there is no copying right now, so set torch, just close all these. Yeah, set torch. Oh god. Python torch.tensor. There is something on the scatamine utils. Now let me just check. Scatamine log exponential scatter. No, not here. Have scatter add softmax, mean max, no, what I need right now is, in whatever order I am given these values, right, I just need to get 1 and 2s from this thing, just to know what are the final values that need to be updated. So I have torch.tensor, this thing I have long, and I get not the unique I have unique torch dot unique. Well, not like this. If I have this, it's going to it's a crazy bastard. No, I don't want it like this. I want unique or dim. Cannot do that is because also I can pass it dim. Interesting. Dim is equal to 1. So 1 1 2 2 1 3 1 2. What? 1 1 2 2 1 3 1 2. What does that? How does that even work? See torch dot unique. Return counts, return inverse, sorted. Ooh. No, I don't want any of that, man. All I need to know is of these particular tensors. Yeah, so you do get 0 0 0 zeros, which is a good sign. But I do need to know in which tokens do I have to fill this, because so we need to add an assert statement which says that the max of this thing plus 1 is supposed to be equal to the second dimension of x. By that we mean that if I am given a lot of embedding vectors, I should have all the edges. There should not be a free node, because no. So you have this, and now all we can say is x orig torch dot where hidden is not equal to 0, pass hidden, else we pass x. Right. Oh, pass x, mate. That's it, motherfuckers. That is it, motherfucker. So you can see minus 1.3 something. You do get minus 1. Oh, what? This is wrong. Oh wait, sorry, yeah. So you have 0.72233 shed, and you have this thing here. And the beautiful thing is, if I just do this, nothing else, there are 4 connections, you see that the x out is completely fucked up. Why? Because I am fucked up. Ah, shit. Supposed to be reducing these values. Asshole. It is not reducing these values. Yeah, so people, I think I need to go for to a meeting right now. I'll, yeah. So we'll probably continue this later in the evening. Till then, goodbye. This is a pretty short stream actually, so it's a pretty useless stream as well because we did not get anything that I hoped we would get done. But who knows? Bye bye.